couple lectures ago, we raised the philosophical question of realism. Physics starts with observation. We see the world around us and we ask questions about it. Physicists derive theories to answer those questions. Those theories include three kinds of elements. One collection of elements are the empirical notions, that is, directly observable terms like mass and distance. A second is formalism, that is, parts of the mathematical grammar like equals sign needed to write out the equations. We know the first group is meant to refer to the world, where the second group doesn't. Mass picks out a property of reality, whereas the equal sign just lets us say something about reality. But then there's a third category. These are what we call theoretical entities. They include things like a gravitational field that's used but not actually seen. They're employed in the theory as more than just mathematical machinery, but they're not directly observable. They, or aspects of them, can be calculated using the empirical and mathematical elements, and they connect the theory in a way that gives us access to additional observable consequences, that is, predictions we can test. But they raise the deep philosophical question about theories in physics. What does it mean when the predictions of a theory are true? What does it mean to accept a theory? Does it mean that we're accepting that the theory is a literal accounting of the furniture and behavior of the world? Now, philosophers tend to divide into two groups around this question. Scientific realists hold theoretical terms to be like observable terms. The realist takes the unobservable parts of the theory and holds them to be unobservable parts of the world. Empiricists, on the other hand, take the theoretical terms to be like the formal grammatical parts of the theory. All that's real is what we can see, and the unobservable terms are just contracted concepts that let us connect the real observable elements in new and clever ways. To accept a theory is to say that the observables are connected in this way, but not to say that the unobservable elements doing the connecting are some literal description of an unobservable reality. There is no unobservable reality. Reality simply is the sum total of what we observe. The theoretical machinery gives us nice ways of thinking about how it connects, but are not to be taken literally. We saw that at the beginning of the 20th century, the theoretical notion atom seemed to give a decisive victory to the realists over the empiricists. It may be true that no one's ever seen an atom, but atomic theory is so successful that it seems absurd to consider atoms as just some useful mental construct. Yet, even in the face of the success of atomic theory, there remained some empiricists who wanted to deny the existence of atoms. They're just silly provocateurs who should be rejected out of hand because of the success of atomic theory, right? Well, atomic theory led to quantum mechanics. And that, of course, is where it gets so much more philosophically interesting. One of my favorite figures in the history of physics is Louis de Broglie. He was studying physics at the Sorbonne when he had what is really quite a simple realization. Modern physics had two branches. There was relativity theory and quantum mechanics. Each has an iconic equation that represented its central idea. For relativity, it's Einstein's E equals mc squared. For quantum mechanics, it's Planck's E equals h nu. So, de Broglie reasoned, if E equals mc squared and E equals h nu, then it must be the case that mc squared equals h nu. De Broglie wrote this middle school level algebra work down, added an 8-page introduction, and submitted it as his doctoral dissertation. Needless to say, it was rejected. But he sent it to Einstein, who read it and vouched for it. Reluctantly, he was awarded his PhD for it, and ultimately also the Nobel Prize. So, mc squared equals h nu. What does that mean? Well, remember that c and h are just constants, just numbers, so it really says mass equals frequency. Equals means it's the same as. What de Broglie is saying is that mass is the same thing as frequency. The strange thing about this is that mass and frequency are properties of completely different kinds of things. Mass is a property of objects. Frequency, on the other hand, is a property of waves. To say that mass is the same thing as frequency is to say that things, particles, are the same thing as waves. What de Broglie had uncovered is what we call wave-particle duality. And it's weird. Philosophically weird. To equate particles and waves seems to commit what philosophers call a category mistake. A category mistake is exactly what it sounds like, putting something in the wrong category. Now, consider two things. A blue chair and the sentence, "the chair is blue." One of these things is an object you sit on. The other is a linguistic thing, a proposition. If I were to say that the sentence is blue, that's a category mistake. Sentences don't have colors. If I were to say the chair is true, that's a category mistake. Chairs can't be true or false. Only sentences can be. It would be a category mistake. Particles are objects. They're self-contained entities. They have a location in space. Waves are different animals. Waves are not independent things. You need a medium to have a wave. If you have a sold-out sporting event, like a football game, you could have the fans do the wave. But in an empty stadium, no wave. The wave and the football may share the ability to have certain properties. If the football is kicked, we can determine its velocity. We can determine its location at a certain time. In the same way, we can determine the velocity and location of the wave at the same instant. But there's a fundamental difference. When the football is done being kicked, it still exists. It's a thing with independent existence. When the fans stop doing the wave, on the other hand, the fans still exist, but the wave does not. If we don't see the football, it makes sense to ask where it went. But if we no longer see the wave, we can't ask where it went. It didn't go anywhere, it just ceased to be. Particles and waves are not only different things, they're different types of things. There are different categories of things. To equate them the way de Broglie did is to make a category mistake. Unless you examine quantum mechanics. Here's where it gets weirder. The suggestion by de Broglie did not come completely out of the blue. Green, yellow, red, or any other part of the color spectrum that was studied by Isaac Newton. In discovering that white light was comprised of all the other colors, Newton posited the corpuscular theory of light, according to which light is made of particles. This was the leading theory until the 19th century, when physicists like Thomas Young, Auguste Fresnel, and George Airy discovered case after case of light acting like a wave. With Maxwell's theory showing that we could treat light as an electromagnetic wave, the deal seemed sealed. Newton's corpuscular theory was replaced with the new wave theory. Light is a wave. And then quantum theory started. As we discussed in the previous lecture, the first theoretical uses of quantum mechanics were Planck with blackbody radiation and Einstein with the photoelectric effect. In both cases, light was treated as a particle when it was emitted or absorbed, but both of them still treated it as a wave when it traveled or interacted with matter or other light. So, which is it really? Is it a wave or a particle? De Broglie says, maybe both. But it can't be both. Which one is it really? And which one is the as if? Recall that the state equation for quantum mechanics is the Schrödinger equation, and that when we solve the equation in a particular context for a particular observable quantity, the result is not a single value for the quantity as we would expect, but rather a combination of every possible outcome coupled with the measure of the probability that the system will be found to have that value. The problem is that we never ever see systems in this superposed state of all its possible states, but rather in exactly one of them. The law of nature tells us what nature looks like when we're not looking, but when we measure it, it changes. This is the so-called measurement problem. It's best illustrated with the famous double slit experiment. This experiment was first carried out by Thomas Young in the late 1800s in his work to support the wave theory of light. So, light from a coherent source is sent through two small slits. These slits then act as if they were light sources. Because the light is coherent, that is, the two waves are in the same phase as each other, When the light hits a screen in front of the slits, there will be a series of bright and dark stripes. This is explained by considering light to be a wave. The color of the light is a function of the length of the wave, and the brightness is a function of the height of the wave. Since the two slits act as light sources for the waves that are synchronized, in the middle the two waves will add. This means that the light will be twice as bright. But move slightly to the side, and it takes one wave a little less time to get there and the other a little more to get there. This means that the waves are out of phase. Move just the right amount to the side, and they're completely out of sync. The top of one will hit the bottom of the other. As a result, they cancel each other out, and there will be a dark spot. Move slightly more to the side, and it will take one even less time to get there, and the other even more time, such that they're back in phase. The result is another bright spot. And so on. As we move from the center, we get alternating bright and dark spots. This result was used by Young to hold light to be a wave. So far, nothing weird. But then, from Planck and Einstein, we know that light is quantized. It comes in packets that can't be divided. We call these photons. Let's run Young's double-slit experiment, but send only one photon at a time. Since it's the smallest unit of light, and we're only sending one, then it'll have a choice. It could go through the left slit or the right slit. Then there would be a single flash somewhere on the screen where the photon hit after going through the slit of its choice. But that's not what happens. When we send the single photon to the slits, what we see on the other side is the striped pattern. But this means that there was adding and subtracting of waves going through both slits. This means that the photon theory of light is wrong. Light is a wave. We need to throw away quantum theory. Not so fast. Let's change the setup slightly. Let's leave the rest of the experiment the same, but add one new measuring device, a photodetector, that will tell us which slit the photon went through. What happens with the new setup? The detector tells us that the photon went through one and only one slit. And what do we see on the screen? Not the alternating light and dark bands, but single flashes of light randomly distributed across the screen. There used to be dark spots, places on the screen with no light, but now there are flashes exactly there from time to time. Now, our lab assistant is a klutz, and in the middle of the experiment, he trips on the cord and unplugs the photodetector. Know what happens the instant the detectors are no longer operative? The light and dark bands reappear. If we look to see which slit the light goes through, then it acts like a particle and only goes through one slit. If we don't look, it acts like a wave and goes through both and adds and subtracts with itself. It knows what we're looking for and acts accordingly. This is the measurement problem in action. When we don't have the photodetectors in place, then there's no measurement of the photon, and it's in its superposed state of going through both left and right slit. That's what gives us the light and dark bands. But when we do have the photodetectors in place, we're making a measurement, and the superposition reduces to just one of the values, left or right, and the result is a randomly placed flash on the screen. So, is it a wave or a particle? You design a test for waves, it's a wave. You design a test for particles, it's a particle. It just wants to make you happy. But you're not happy. You're befuddled. Which is it really? Waves and particles are different kinds of things. It can't be both. As if that wasn't bad enough, it isn't just light. We tried the same experiment with electrons, same result. We tried it with complete atoms, same result. We've even succeeded in doing it with molecules, same result. Matter may not be matter. Stuff might not be particles, but waves. Not weird enough yet? Okay, let's take another step. Suppose you have a pet electron, Lucky. You've had Lucky your whole life. Lucky was with you through thick and thin. One day, walking down the street, you accidentally bump into someone and drop Lucky. Unfortunately, that person also had a pet electron, and the two bounce off of each other. Now, there are two electrons lying on the sidewalk. You go to pick up your beloved Lucky. But which one is it? The interaction has caused the two electrons to become entangled. Despite the fact that you know lucky as well as you know anything in the world, there is no way to tell which of those electrons is lucky. Quantum entanglement means that all that exists is the system. There's no way to differentiate the parts. There is no fact of the world anymore about which one of the electrons is your pet lucky. Your electron has lost its identity. But identity is the defining characteristic of things. To be a thing is to have an identity. The 13th century Scottish philosopher Duns Scotus coined the Latin term haixity, which translates to thisness, to account for the most fundamental element of identity. A thing's haixity is that which differentiates it from every other thing in the universe. Identical twins may be perfectly identical, having every other property in common, but they will each have their own haixity. But that's exactly what's lost with quantum entanglement. You were never quite able to figure out if lucky was really a wave or a particle. But now you can't even figure out which electron is your lucky because there is no electron that is your electron lucky, even though there was before the accident. It looks like you are now truly unlucky. And if that isn't bad enough, you're also a realist. You've long believed in the reality of atoms, but now, without lucky in your pocket, you aren't sure what to believe anymore. Welcome to philosophy. Recall that we have a debate. On one side are the empiricists. Empiricists live by the motto, seeing is believing. If you can't observe it, it's not something you consider to be real. Scientific theories are collections of rules for computation of observable outcomes, predictions. Good scientific theories are ones that give us good predictions. What's under the hood doing the work, generating the predictions, is just mere machinery. Pay no attention to the man behind the curtain. On the other side are the realists. These are thinkers who hold that the reason our best scientific theories are so good at producing successful predictions is that they're accurate descriptions of the underlying reality itself. Science is an amazing thing because what it does is allow us to see the invisible. When we have an acceptable theory, it teaches us about the nature of the world beyond our observations. We saw that atomic theory seemed to hand the trophy in this contest to the realists. Given the successes of early atomic theory, we surely had to believe in the existence of atoms. But atomic theory developed, and that development made the question much more complex. The group who began philosophy of physics, the logical positivists, were committed empiricists. All meaningful statements had to be logically reducible to protocol sentences, statements of the form read here now that accurately report direct sense perception. While their views suffered under the success of atomic theory, they fully recognized that quantum theory seemed to vindicate them. Gustav Bergmann was one of the younger members of the Vienna Circle of Logical Positivists. A philosopher, mathematician, and physicist, Bergmann worked briefly with Albert Einstein. Because he was Jewish, he had to flee the Nazi invasion of Austria and lived out his life as a professor of philosophy at the University of Iowa. In his article, The Logic of Quanta, Bergmann takes quantum mechanics to be a quintessentially empiricist theory. The theory, he argues, is a collection of rules governing measurement. Measurements are the results of observations, and what the theory does is tell us about measurements. Are light and subatomic constituents really waves or particles? This isn't the sort of question science deals with. There is no really here. The only really there is the world of measurement. Is there a measurement problem in quantum mechanics? Well, it's only a problem if you're a realist. If you have a governing principle, the Schrödinger equation, that when you solve it provides a superposed set of possibilities with each possibility multiplied by a coefficient that's a measure of probability that it will be observed in that state. When we observe the system, we never see the superposition, but only the system with a single property value. And it's impossible to predict with absolute certainty which value it will be. This seems to violate causation. And surely causation is the foundation of physics. But Bergman is not bothered by any of this. The theory is successful because the Schrödinger equation does give us the correct statistical data about the measurements we will make. Causation is a metaphysical notion that's only required if we're trying to see the invisible forces underneath observable reality. But if we're willing to jettison the metaphysics and make science responsible only for correlating our observations, then quantum theory provides us with no concerns. The problem with the seeming weirdness of quantum mechanics comes from the desire to have a realist viewpoint. If we're willing to give up the reality of atoms, then the progress in atomic theory can be seen simply as progress. But we hate to give up realism. If our best theories make use of an unobserved entity and it's incredibly successful at generating explanations and successful new predictions, then, the realist argues, it would be a miracle if the world were not really that way. The problem for realists posed by quantum mechanics is that it says things are both waves and particles when they're completely different categories of things, and so something can't be both. It had laws of nature that only work when we aren't looking, but are violated in ways we can't predict as soon as we do look. It would be a miracle if nature really was this way. How can one hold on to a realist viewpoint when the most successful scientific theory doesn't produce a complete, coherent picture of the underlying reality? The champion of scientific realists was Einstein. He was a pictorial thinker, working from images. He would code them mathematically after the fact, but physics was the activity of making sense of the underlying reality that generated the measurements. Determinism and causation were assumed elements of the nature of the underlying reality. Quantum mechanics denies these. Einstein realized that he could have realism or he could have quantum mechanics. He refused to give up his realism. Atoms exist. Bergman is right about the theory just being a system of correlations of measurements. But science is supposed to do more. So, Einstein held that quantum mechanics is incomplete. It's not a finished theory. It's a useful theory as a provisional placeholder, but unsuccessful because it doesn't allow us the realist picture of the underlying reality. That reality is mechanistic in its workings. This is what Einstein meant by God does not play dice with the universe. There's no probability allowed in a finished theory. The picture has to be absolutely determinate about everything and show how it comes to have the values it does. Quantum mechanics can't do this. So, in order to maintain his philosophical position of scientific realism, Einstein refused to accept quantum mechanics. Contemporary philosophers have attempted to thread that needle. The hope is that accepting quantum mechanics and believing in atoms are not mutually exclusive. One thinker who tries to make this work is Arthur Fine, professor of philosophy at Northwestern University. In his book, The Shaky Game, Einstein, Realism, and the Quantum Theory, he looks at the realism-empiricism debate around quantum theory and tries to forge an intermediary position. His view is what he calls the natural ontological attitude, NOA, which he pronounces Noah. The goal is to weave a path that winds between realism and anti-realism, a path we could think of as Noah's Ark. The key to Fine's argument is the contention that both the realist and the anti-realist start from the same place, what he terms the core position. The core position is the common sense sort of acceptance as true that we have for well-supported theory. If I ask you if atomic theory is true, you'd probably say yes. If I then became an obnoxious philosopher and followed it up with, so, you say that you think atomic theory is true. Tell me then, exactly what do you mean by the word true? You'd be confused for a minute, fumble for some way of clarifying that which is already clear, and tell me this is why everyone hates philosophers. But trying to answer that obnoxious question that doesn't seem to need an answer is exactly what philosophers do. Both realists and empiricists contend that the question needs answering, but they give very different answers. The theory of truth is an addition to the core position. Both realism and empiricism are core position plus, but they add very different extra ingredients. Realists have what philosophers call a correspondence theory of truth. What that means is they hold that a sentence is true if it corresponds to the actual state of the world. Consider the sentence, Steve is wearing a tie. The sentence is true because what it says about the world is the case in the world. Steve, tie, wearing. What puts the real in realism is the metaphysical claim that science somehow gives us access to the invisible underlying reality. In order to know if there is or is not the requisite correlation between theory and world, you need special access to the world. But that's exactly what's at question here. Why should we believe that the elements in a scientific theory are meant to point to elements of reality when we can't observe them? We don't know if they exist. To simply assert it is to beg the question. That is to assume the thing we're trying to show. The core position plus of the realist takes the theory and extends it further, beyond what we're justified in believing. The empiricists see this overextension, what Fine terms the sin of metaphysics, and, he argues, overcorrects for it. The theory of truth that we see added to the core position by the empiricists is reductionism. That is, a view that a sentence is true only if it reduces to protocol sentences, observation reports. This addition of a theory of truth to the core position has the effect of restricting the beliefs we accept as true. When we apply the concept of truth to the theory, we fail to overextend as the realist does, but as a result, we lose what seems like perfectly reasonable beliefs. Fine's Noah says, I like my interpretations of scientific theories the way I like my food, with no additives. What was wrong with the common sense core position? We all agreed on it as a starting point. Why bother making the additions? The realist and the empiricist say, because as philosophers, it's exactly our job to give an account of what concepts like truth are. And doing that answers the philosophical questions that do come out of physics, like, do atoms exist? Fine says, we can do that, but it shouldn't be dictated by the philosophers down to the physics, but pulled by the philosophers out of the physics. The science will be our guide. In the case of quantum physics, we have two concerns. On the one hand, the realist points to atoms, electrons, protons, quarks. Fine calls it an entire zoo of particles that comes out of the theory. We want to think that the success of the theory gives us reason to believe in their existence. On the other hand, the anti-realists point to wave-particle duality and the superposed states that are never observed and seem to fracture our minds if we want to argue that there is some kind of metaphysical correlation we have magical access to, which perfectly describes the actual state of the invisible reality. Realists seem to have to buy the latter to give us the former. Empiricists throw away the value of the former to rule out the latter. Fine's Noah tries to have its metaphysical cake and epistemologically eat it too. The idea is that what the core position alone gives us is reason to believe that which is controversially necessary in understanding the theory. The theory clearly says there are electrons, so there are electrons. We believe it. Are they waves? Are they particles? Are they wavesicles? It isn't clear, so we suspend belief. Are they really spread out through space when we don't look? Don't know, so we don't know. Is this common sense approach too easy? Some think so. But while this may save us a headache, it also seems to bankrupt science. Do we want science to give us reality? Or do we want to eliminate the problems that come from taking what science says seriously? No one said philosophy was cheap. Philosophers? Yeah, we're cheap. But philosophy? Well,